I'm glad to be here. I've had a tremendous amount of fun with smearing. And it's something that you've probably done yourself inadvertently. But I like to start out by telling people that working in this business, handling human waste, is like wearing a dark suit and wetting your pants. You get a nice warm feeling all over, but nobody else seems to notice. So let's look at some history. I was asked in 1995, well actually I went into Mount Rainier National Park and asked them if there was anything in human waste management that they were interested in looking at. And we did a snowfield examination where we looked at the water, free-flowing water over the snowfield. They actually, at Mount Rainier, for the dehydrating toilet at Muir, released the urine to the underdrain of the snowfield. And they wondered if this was going to pop up in the fresh water. Then in '99, we did a study of smearing on rocks in the snowfield. And then based on that, we did a study of smearing in a temperate rainforest environment and in an arid environment. So we're going to look at all of those. And this was a cooperative project, not really expensive, but we had NOLS, Leave No Trace, Forest Service, National Park Service, and the university that I was working at. So this is the Muir snowfield. Camp Muir here at 10-2. There were some fill fields that would will eventually break out here that had water flowing over them. So we know that there was a lot of visitors that used that water untreated. And so we set up a study to look at the microbiological contamination. And that was basically fecal microorganisms, fecal coliform, fecal strep, E. coli. Want to look at Pseudomonas aeruginosa, chloride, and total dissolved solids. Now, the problem is with chloride, the precipitation that falls on Mount Rainier comes a great distance over the ocean. And so whatever chloride we found was largely from ocean spray. So we found no bacteria. So the question became, where did it go? You know, we want to sanitize this as much as possible. So the folks in GIS at Mount Rainier did a predicted flow path analysis and found out that where we were sampling, primarily over here, was way away from where the predicted flow path was. So we were probably sampling in the wrong area. But that's okay, everybody makes a mistake. So when the urge strikes, here, the trail to Camp Muir, and what a lovely picture. 2 days later, I went back up to establish some sample sites, and this is the climbing community. The trail moved about 2 feet away. Nobody cleaned it up. Nobody buried it. By the way, I have seen mini pads, women's mini pads disposed of on the surface of the snowfield as well. So there was no history of public health data to support smearing, and that's what the Rainier folks wanted to look at. So I said, well, since there is none, why don't we take a look at smearing and see if that would be a good thing. So in 1999, we wanted to see what would happen to feces and fecal microorganisms that were deposited in the alpine environment, and looking at smearing as a potential method. So in the first part of the study, we set out 6 specimens. I named these 2 deep, 2 steep, and 2 flat. And these were actually an elimination from me, transported in a, oh, just a minute. Transported in a Ziploc bag. Now, these were not fished out of a toilet. This was direct deposit. And what I'd really like to do sometime is try snack bags. You've seen the Ziploc commercials where they hold tomatoes or spaghetti sauce over the aquarium. You know, these are safe. So far they haven't responded to a letter saying, this is what I used your bags for. Would you like to hold it over spaghetti or something like that? So anyway, we looked at deep specimens. Here, what we wanted to do is after the sample was deposited, we wanted for a long period of time to try to look at the snows beneath the fecal material to determine the rate and the extent of the downward migration of fecal microorganisms on a steep surface, or on a deep surface. On steep, we wanted to see if they moved away from the fecal mass quickly, and on flat, we wanted to look at whether they migrated out. So, plop, plop, fizz, fizz, oh, what a relief it is. Here is a fecal specimen. And the thing to note is how I'm so proud. How quickly a brown stain leaches away from this. Now, here, after almost 3 weeks, notice a couple of things. First of all, notice this gray area. That's extreme desiccation. And then also notice that these are acting as a black body, retaining heat a little longer. And so they will self-dispose, I guess you could say. It's just like a fecal material digging its own cat hole in the snow. That's the good news. The bad news is in July, a snowfall buried all 6 samples. So we had to go back and start the thing all over again. Well, that's okay. Stuff happens. We took samples, we analyzed them within 24 hours using standard methods for fecal coliform, E. coli, fecal strep, and Pseudomonas, which is a pathogen. We determined that fecal bacteria are washed off to the snow, the surrounding snow, but it does not appear to last very long, and it's not particularly extensive. You can see below here 6 inches, some fecal coliform, fecal strep, down 12 inches, some fecal coliform and fecal strep. So it does, material does wash off. This was not a tremendously long study, so we don't know for how long this occurred. If we look at the steep specimen on a steep part of the snowfield, notice that upslope, no detectable fecal organisms, downslope, no detectable fecal organisms, nor to the side. So slope apparently doesn't have make any difference. Also, wind, as you'll see in a little bit, apparently plays little to no role in the translocation of fecal microorganisms. Now, there's a really, really good reason for that we'll be getting to. Same way with a flat specimen, it just seems like, except for this lone 2 colony-forming units for fecal strep, that after 41 days of exposure, there's not a lot of transmigration of the organisms. Now, here's an indication of fecal organisms in feces, not on the snow, but a sample taken from inside the fecal material. And you can see that over time, fecal microorganisms gradually decrease. And we would normally expect to see that. Another internal specimen where we have orders of magnitude from 1 million to 10 million per gram, and after a 1 or 2 month period of time, let me back up just a second. These are fecal organisms that are on the surface of the fecal mass. Now notice the slope of the curve. Here are fecal organisms within the fecal material. So the die-off on the outside of the fecal mass is much more rapid than the die-off of the organisms inside the fecal material. Fecal strep do have a tendency, as has been shown in a lot of cases, to survive longer. A flora deep within the specimens will survive longer. And that makes a lot of sense. So basically, we have to realize that they can survive in the alpine environment, but that those on the surface decrease significantly faster. It acts as a black body and sinks into the snow, but specimens during our study never completely disappeared unless they were covered with new snow. Now, this was interesting to us because here's the 1st of August, 1999, and the fecal specimen had broken into 2 parts. Here, it had broken into 3, and by September, it had broken into more than 12 separate pieces. Now, what I want you to know is that when we examined all this little stuff here for microbiological content, there was none. There were no fecal coliform fecal strep. So the assumption is that as the fecal mass is desiccated, the winds will blow, erode materials from the mass, and by that time the fecal organisms are dead. We also tried smearing. We made a pancake veneer on a rock, thin and thick. By the way, within 20 minutes we had flies visiting the smears. But within 20 minutes, this had visibly darkened and desiccated. So, whoa. So here's after 2 weeks of exposure, you can see what's happened to the mass. You probably did not expect to see this.
But it's not here, where?
40 days of exposure, the smear actually had been blown off of the supporting rock. We also took a look, we examined the soils around before, during, and after smearing. And it's hard to see here, but the fecal mass has disappeared. Here, some of the flakes are still there, including a kernel of corn. Memo to self, chew more completely. You guys have got to take this more seriously. So smears desiccate. Okay, we can see that. The exposure time of the smears in the alpine zone was 56 days, 8 weeks. Here we can see some graph of that particular data, and when you see something like this happen, then you have to start correlating it with the weather, and that was, I mean, if you've got an organic mass on a rock and it rains, that organic mass is going to absorb. It's going to act like a sponge. Don't use it for a bath, but it could act like a sponge. Now, within the smears themselves, now this isn't the fecal mass on the snow. This is the fecal mass on the smear. Notice that there was a very rapid die-off. And in fact, in the case of E. coli, it went to 0. So they began desiccating immediately and virtually disappeared. Now that may be good, it may be bad news. Soil contamination was nil. So the assumption is that organisms succumb to environmental conditions prior to the breakup and the disappearance of the fecal mass. So what are the public health impacts? Well, first of all, viruses probably don't survive any longer than the bacteria because they're obligate intracellular parasites, and if the bacteria are gone, if the bacteria are dead, they're going to be dead. But protozoa can survive long times, especially in the alpine zone. So that's a problem. The suggestion was to continue the study to verify the results, so we did a couple of other things. To add a temperate rainforest component, to add a drylands component, and to investigate the possibility of including protozoa. I can tell you right now that we didn't do that because that requires a tremendous amount of other associated laboratory equipment. So we just couldn't go there with the funding that we had. So in the 2000 study, we did the temperate rainforest and the arid lands experiments. So the temperate site was near Longmire, inside the southwest entrance of Mount Rainier National Park, and classified as a wet, humid, shady, heavily forested area. And I chose this area because we have a cabin south of there, and I could live there cheaply. So here's Mount Rainier National Park, the Longmire site. Here's Longmire, the bridge over the Nisqually River, and this is the Longmire wastewater treatment plant. So it's very, very convenient. This is where I did all of the, or that's where all of the microbiological studies were done. And that was my, oh, by the way, that was my lab, my field technician. I hired her over the phone, and she had one question for me when I got there, and that was, how am I going to control and poop on each rock? I said, well, first of all, we're not going to use your poop. We're going to use my poop. So you can see this is a very forested area. The second one was outside of Yakima, Washington, a little town called Natchez, and it's we got access to a locked area. It's very hot, dry, little rain. It's in this particular area here, and let me get to that particular very dry area. So, and it was so far off the road that my field tech would actually stay there, camp there at night, take the samples in the morning, and then leave. Okay, one of the things that I did not mention the last time was that when the smears disappeared, we did not know if that was due to weather. It may have been due to something referred to as a coprophagous animal, or a shit-eating animal. So, there's only one way to solve that particular problem, and that is to put the smear-containing rocks in dog crates covered with hardware cloth. I've got a really good story I won't go into about buying dog crates for this in Petco, but we won't do that right now. Within each crate, we put 2 thick smears and 2 thin smears. We sampled only one of the thick and one of the thin at each site for microbiological analysis. The other, we simply looked at weights. The reason that I wanted to leave some of the smears alone is we wanted to make sure that the weight loss was due to natural causes and not because we chopped parts of the fecal specimen off. So here we are. We tied these down to hopefully prevent them from being blown around. And here are our little veneers. And so some of these we consistently wanted to sample some and leave some others undisturbed. Our samples here were set out because we didn't have to carry these dog crates up into the alpine area. On the 3rd of June of 2000, took biweekly weights and fecal specimens. Final micro samples were taken 14 weeks later, and the final weight data was taken 18 weeks later. So this was a much longer study, 10 weeks longer than the Alpine study. So the rocks, basically the method that we used with the rocks were tear weight. Yeah. When I gave this presentation in Washington State, I pointed out that that's my Wazoo, my Washington State class ring. You can see the cougar through the gloves. Okay, notice here that after the second day, the Natchez site, the dry site, was desiccating tremendously. And at Longmire, the only thing that happened is that flies were able to get through the hardware cloth and deposited eggs, and so we had a lot of larval activity. And then a few days later it rained, so we had little rivulets of shit containing water flowing off, which was all right. 4 weeks later, Natchez and Longmire. The interesting thing is, as this whole study continued, the Natchez sites really took on the appearance of a sponge, where the Longmire sites kind of collapsed. The fecal material kind of collapsed into a much more dense mass. At least I thought it was interesting. And with the Longmire site, we also had some really funky mold starting to grow, and you can see some of the hyphae and sporangia there from the mold. Okay, after 18 weeks, this is what one of the Natchez specimens looked like. Did you notice the corn? I can't chew that. Anyway, this is the Longmire site. I've got to chew my food better. Corn. Good old Yakima corn, I'll tell you. Okay, results. In both cases, they wound up, while they appeared very different, they wound up weighing or losing about the same equivalent amount of weight. Weight loss over time, and here again you can see that the Longmire, where it rains a lot, may have gone through a dry period, but boy, when it started raining again in September, the fecal mass would absorb the moisture. The masses were different, as I described. On the dry side, they were dry, sponge-like, and fibrous. Oh, yeah. At a Longmire, they were flat and non-fibrous. This is probably more than you really wanted to learn. Okay. Because the rocks really retained the fecal mass, one of the assumptions was the smearing experiment on the snow field, where the smears disappeared, that was more than likely due to coprophagous animals, both mammals and birds. Initial samples of soils were taken. Following those initial samples of soil, there was no contamination before smearing. After smearing, we found on the dry side one bacteria, one contamination one time. But in Longmire, where we had a lot of rain, 3 of the 7 sample sites, or 3 of the 7 sample days, we had fecal contamination in the soil. And these numbers decreased, but there was lots of contamination. You saw the brown rivulets of water running off. From the 700s to 30, there's just wild fluctuation. I'm not sure why that fluctuation is. Maybe because within a fecal mass, there may be different concentrations of organisms in different parts of the fecal material. It may be that there's different pathways through the soil, and some of these will transmit or transport microorganisms more rapidly. But here in soils, you can see there was a big bump, but for the most part, there was little runoff. And here, the red lines are the dry side, the black lines are Longmire, and boy, wherever it's black, it's Longmire, and rain contributed to this translocation of the microorganisms from the fecal material to the soil. So if we look at survival in soil, E. coli, because it is a fecal microorganism, and this is not the enteropathogenic E. coli, but still doesn't survive well because conditions aren't good for it. Let's go back to that. Fecal coliforms does survive more than E. coli, but fecal coliforms do not survive longer than fecal strep. Fecal strep just generally can survive longer in both a soil and a water environment than E. coli and fecal coliforms. Okay, organisms inside the smears, here's Natchez, here's Longmire. So if you're going to smear and you want bacteria to die, don't try smearing in a humid, temperate, shady environment. All right. Fecal microorganisms fluctuated on the dry side. E. coli was detected only one time, so the E. coli within the smear disappeared very, very quickly. At Longmire, there was substantial survival within the smear during the entire study period, to the point where at the end there was 384,000 per gram fecal coliform, 706,000 per gram fecal strep, and 436,000 per gram of E. coli. So that's a pretty tenacious survival. Well, let's get to some of the other stuff, because I've got some movies I want to show you. Survival comparisons between the dry side here in the front and the temperate side. Okay. In an arid environment, you're going to get much more rapid die-off, more than likely due to, as we've learned a little earlier, temperature, humidity, and solar radiation. That's probably, I mean, the UV in the alpine areas probably what did a lot of the damage to the microorganisms on the surface of the fecal specimens there. All right, let's see. Well, this will all be on the stuff that will be made available. Public health impacts. Again, it wasn't our intent to look at protozoa, it wasn't our intent to look at viruses. And so viruses can survive as long as bacteria. So if you've got viruses in Longmire in a humid, moist, shady environment, these organisms are lasting for 10, 12 weeks. You're going to have viruses lasting that long. Protozoa will last even longer. Smearing may be, I think this is important, it may be okay under some environmental conditions, but I think what you have to realize is that in these studies, it was smears from one person. Now, if you've got the Wonderland Trail going around Mount Rainier, and there are hundreds and hundreds of people using this thing, there probably will not be enough rock to support. Well, they might try that at Rocky Mountain National Park in the boulder field there. You could use, multiple people could use one rock. Have to realize that if we spread these to water, or if animals consume this material, animals may transport this material. Also, I think we have to look at the seeds that are within human fecal material and the potential of spreading them to areas as a non-indigenous or an exotic species. So it's deceptively simple. It's easy to do. You don't really need a spatula. Finger painting. Very good. Hadn't thought about that. I really think, well, I made my own poop tube out of PVC plastic. It's really simple to produce. We've got a lot of stuff to learn still about smearing. We know what happens to fecal mass is deposited whole on the snow field. But would the same thing happen to a snow field smear? Smearing on the snow? So we decided to do that on the 29th of July, 2000. So it's supposed to work. Oh, come on. All right. Let me go back to that. All right. Let's see if it'll self-launch. Well, we wanted to do this two different ways. Darn, this worked on my computer. Fecal specimen, snowball. Could we use just a ball of snow to do that? But it didn't work because the feces kept sticking to the snow. Darn, didn't work. And so Joy had her specimen. By the way, I want you to notice that's a 1-gallon plastic Ziploc. Then I used a sandwich bag. So that's, in terms of confidence of hitting the target. It is much easier to spread using the Ziploc bag as a glove. So we started sampling the smears immediately again. They had a little slope to the snow field, and so the no corn. We had the stain. We had fecal coliform in the stained snow. We had E. coli, no Pseudomonas, no fecal strep. So 2 weeks later, we took snow samples, no detectable fecal bacteria in aliquots of up to 50 mLs. And following August 11th, 2 weeks after smearing, the fecal specimen had totally disappeared. Which may be good, may be bad. Maybe due to coprophagous animals. I'm assuming that in this environment it probably was. So it may be, smearing on snow may be better than simply dropping fecal material on snow. A 1995 report on the surface water runoff. There's one on smearing in the alpine zone from 1999. There is a 2000 study on in the arid environment, and there is a 2000 study on the temperate environment as well.
I read your 1999 report about 3 or 4 days ago, and the pictures were great.
Thank you.
There was a lot of them.
More than here.
Yeah, and I pretend like I manage Camp Muir now, and I've worked there for almost 20 years on and off for most of that time, and there's a long-standing misconception maybe that you're clearing up for me right now, and by reading the report that, people have this impression that the snow just all over the place up there, you know, people call Camp Muir a frozen cesspool,
Yeah.
basically. And it's, by what you're describing and what I read, actually, that it's not actually as bad.
No.
Or it's potentially not as bad, because you weren't working at Camp Muir with these studies.
No, I visited a few times. The interesting thing to me that just outside the door of the public shelter is this little mound cone of yellow snow, which
Still
is-
there.
It's indicative to me that people don't want to go too far to pee. They'll go a little farther if they have to take a crap, but they won't go too far to pee.
One of the assumptions that people always talk about is the fact that since, you know, there's brown snow in a lot of places,
Yeah.
there's stuff that we pick up that people leave. You know, people walk on this, and that is a vector for actually spreading it as well.
Absolutely.
And so, but by what I'm seeing, that's very similar to smearing. You know,
I'd thought about
translocating
that.
it by walking. It seems like, you know, in 2 or 3 weeks, if that was a vector for a particular specimen, then it might be gone in that amount of time. Now, is that, you said coprophagus,
Coprophagous animals?
Animals.
Cool word.
but what about UV?
Well, UV plays a huge role in the alpine environment and a significant role anyplace else. In the arid environment, we probably had a lot of fecal die-off because of high UV, no clouds. But at Longmire, it probably didn't play as much of a role because it's cloudier there. So, but in the alpine environment, you've got extremely low humidity, you've got cold, and you've got UV exposure and wind. And all those are going to be bactericidal. So, but they're going to be bactericidal to the surface of a mass. So, you know, in that respect, making the mass as thin as possible is a good thing.
What happens to all the poop that gets snowed on?
You know, I'd say that's probably a lot like a cat hole. It's buried, it's down there. I'd say it may be better in terms of thermal, the cold destroying the microorganisms. At least it's fairly well encapsulated. Because at least the snowfield, not like Denali and a lot of other places where you're depositing in a crevasse, and that could be an escalator, as it were, for human waste. The snowfield apparently is a snowfield because it's not moving. If it was, it would be a glacier.
Say that this work is why we rewrote our rock climbing curriculum, because how many people are going to put a gallon-sized Ziploc on their hand? I mean, I'm sure your research tech has PTSD. How many people are going to do that and actually smear waste in that fashion? There is solid rationale, I think, for us not recommending this to the masses, because it gives people an easy out just to take a dump and leave this black mass just sitting there on the surface. So that again, was largely based on this work, is why we revamped that. But as you can see, in certain environments, it's possible that it could be a solution.